Hello everybody, we are going to tackle Module 11 today, the chemistry of solutions, page 353 in your textbook. We're going to go all the way to co-pack, so we're going to stop just before applying stoichiometry to a solution. No math this week. Lots of experiments though. We have 3. So what are we covering in this module? How solutes dissolve in solvents, solubility, applying stoichiometry to solutions, molality, and the boiling point elevation. Today we're going to cover the first 2. Need to know the definition of solute, solvent, and solution. There's a lot of repetition, so hopefully by the end of this module, not this module, the first half of the module, everything is going to make sense to you. And this sounds similar, so be careful, okay? Solute is a substance dissolving. It can be a solid, a liquid, or a gas. Solvents also can be solid liquids and gases, but the difference is that the solute is the one in the smaller amount that you put in the solvent. In this case, you have a solid solute dissolving into a liquid solvent, but it's not always the case, as you will see. When you have the mix, when you have dissolved them, you have a solution. So you have a solute dissolved in a solvent. That's a solution. Know the definition for each, please. So page 357, they give you examples. I said to you that solutes and solvents can exist in any phase. Solute can be solid, a gas, and a liquid. The solvent also can be a solid, a liquid, or a gas. Okay? Give me examples of each. So solute is a material being dissolved, usually the lesser amount. The solvent is the material doing the dissolving, usually in the greater amount, and when you have them together, you have created a solution. Here's an example of both solid solute and solid solvent, when you create alloys between metals, brass and steel, for example. An example of a solute that's solid and a solvent that's liquid is when you create salt water, or maybe when you put sugar in your tea, for example. A gas that is a solute in a solvent that is a solid, when you put air bubbles in an ice cube. A liquid with a liquid, mixed drinks, maybe when you put, I don't know if you ever have to, you're trying to put alcohol in water, they dissolve one another, mix each other. I don't know why you would do that, but you can do that. A gas with a liquid. Gas, CO2, you put in a liquid that is a soft drink. You create soda. So sugar water, actually that was a solid in a liquid. And when you have that solution, you can put the gas in, as you see in a minute. The example of lemonade, we'll see in a minute. Or gas in gas, the air around you, you already know that it's made out of many, many gases. Nitrogen, the most abundant, is then oxygen, but there's also carbon dioxide and other kinds of gases. And all together create a mixture. That's a solution of gases. So now at least an example of each kind. Solid with a solid with a liquid, a gas with a gas, a liquid with a liquid, and so on. Another example, to make sure that you understand that a solution can then be mixed with another thing and create another solution, and mixed with another thing to create a new solution. So for example, liquid dissolved in another liquid. You have lemon juice is your solute here. Dissolved in water, water is your solvent. You have created a liquid solution of lemon juice and water. Okay, great. Next step. Now you want to put sugar to make it pleasant to drink. So that sugar is your solute. That's a solid solute that you're dissolving in a liquid that was created with lemon and water. Lemon water now is your solvent. So you have to be able to distinguish who is the solute here, who is the solvent here, what am I creating, what kind of solution I'm creating. Be able to think this through. Great. Now somebody likes bubbles in their lemonade, okay? Kind of a soda pop experience. So you can dissolve gas in that sugary lemon water that you created. The CO2, the gas, is your solute. that you're dissolving in a solvent that is the lemonade that you created, and you're making sparkling lemonade. Now, this is done a bit silly, but when you're drinking that lemonade by the lemonade stand, you are surrounded by a solution of gases. Oxygen and nitrogen is mostly what is in the air that you're breathing. So you have a gas in the gas example there. What happens when a solute dissolves? You need to be able to explain to me what is going on. Now, there are attractive forces between the solute particles holding them together. So here you have table salt, sodium chloride. Between them, there are attracting forces. There are ions, positive, negative, attracts one another, is keeping them together to form that ion. There are also attractive forces between the solvent molecules. Here you have your water, is your solvent. Between water and water, there also are forces keeping it together. The negative is attracted to the positive here, and so on. When we mix the solute with the solvent, there are attractive forces between the solute particles and the solvent molecules. Here they are. The positive side of this polar molecule is attracted to the negative ion. The negative side of the water molecule is attracted to the positive ion. So there are forces of attraction. If these forces of attraction are stronger than the attraction between the ions, it will break the ions apart. It will dissolve that solute of table salt into the water. And let's move on. In a minute you're going to see another PowerPoint that shows how that happens. But before we do that, we need to talk about likes dissolves likes. Who can dissolve who? Okay, that's on page 357. In this case, like refers to polarity of the solute and the solvent. And you have this table in your textbook, so follow along, page 357. Not only do the forces of attraction need to be strong enough to dissolve that solute in that solution, but there are also rules of who can dissolve who, and they should make sense to you. A polar solute is attracted to another polar solute. If there are charges, there's going to be attraction. And if it's strong enough, it will dissolve. Ionic solutes also have charges. So polar solvents can attract ionic solutes. When you have a non-polar solute, so covalent compounds that don't have any kind of charges, they are not going to be attracted to a polar solvent because there's no attraction there. There's no charges to attract each other. But they will dissolve and be attracted to other non-polar solvents. We're not going to tackle this right here very much. We're going to talk about it like non-polar solutes dissolve non-polar solvents, like oil and gasoline will dissolve one another. But we're not going to go into the why that happens in this course. If you take advanced chemistry next year, you can learn how it happens. Okay? And once again, a polar solute is not attracted to non-polar solvents. There is no charges to attract one another. Ionic solutes are not also, they are not attracted to non-polar solvents either. So know how this works. And be able to give some examples. So water will dissolve salt. So water is a polar solvent, and the salt is your ionic solute. So it does work. There's attraction between the two, and one dissolves the other. Water will also dissolve sugar. Sugar is a polar solute. So polar and polar are attracted to one another, and it will work as well. There's going to be a solution that's going to form between the sugar and the water. Okay. Now, let's look at these figures 11.1 and 11.2 and 11.3 in your textbook. How does this work? Here you have your table salt dissolving in a polar solvent, water. the first step is for that water molecule and that water molecule right here to penetrate the ions and pull them apart. That's the first step. So water is able, the attraction between the ions and the water is strong enough to take those ions apart from this solid crystal right here. Once they have done that, once they have pulled those ions from the crystal, then they surround those ions according to likes. Who likes who? So charges that are opposite attract one another. So here's your water molecule. There are 4 of them right here. Facing the positive side of the molecule is facing the negative chlorine, because positive attracts negative or negative attracts positive. So surrounding the molecule according to likes of charges. Here you have your sodium ion that was pulled apart from the crystal. Who surrounds what side of the molecule of water is surrounding that ion? Well, the negative side of the water is surrounding that ion, because charges that are opposite attract one another. And you need to be able to explain these, the steps. Breaking apart and then surrounding according to likes of charges. Here's another example. It's the same thing. Remember the first step? So you need to be able to explain this right here. The first step is pulling the ions from their crystal solid form. It's not always possible for water to pull apart an ionic compound. Okay, just know that sometimes the forces of attraction between the ions is stronger than the attraction to the water molecules. And if that happens, then the ionic compound will remain as a solid. And we'll see in a minute. They have names. This, when you don't dissolve, it has a name. And you're going to learn about that. But you need to be able to explain how water dissolves salt. Now, water is also called the universal solvent because it can dissolve ionic compounds and it can dissolve polar covalent molecules. You already know that water is created with oxygen and 1 oxygen and 2 atoms of hydrogen, and that it is a polar covalent compound, meaning these covalent bonds between the oxygen and the hydrogen. And you also know that oxygen is more electronegative. That means that those electrons spend more time with the oxygen, creating partial charges on opposite sides of the molecule. They make a band shape. The geometry is band with an angle of 105 degrees. All of this you have covered. And the fact that it has partial charges makes it a universal solvent. Now, soluble versus insoluble. So when a solute can dissolve in a solvent, we say that that solute is soluble. The substance will dissolve in that liquid or whatever. Okay, so there you go. The water is surrounding those ions or that polar covalent molecule, whatever it is. But sometimes it doesn't. It does not dissolve. So when it doesn't dissolve, you see that that solute is insoluble. It will not dissolve. That substance will not dissolve in a liquid. And then what happens? It precipitates. It just, here's your beaker. It's not floating around here. It's not dissolved. It's not surrounded by molecules of water. It just falls down. Page 355 has a definition of both. Now, we saw an example of the water, the universal solvent, or a polar covalent molecule solvent, dissolving an ionic compound. And you have ionic, when you have ionic compounds dissolve in water, the ions can conduct electricity. You have charges that can conduct electricity. Okay? But sometimes your solute is not an ionic compound. It's another polar covalent solute. And we'll see table sugar in a minute, but here's another example. Okay? This molecule has phosphorus and it has hydrogen. It has covalent bonding between them and is polar, meaning those electrons spend more time with the phosphorus than they do with the hydrogen. When you have one of these kind of solutes, okay, the water molecule does not break the covalent bonding. It cannot do that. It's not strong enough to break it apart. So what they do is they break the molecule as a whole from the solid and then surround accordingly. The side of the molecule that's positive is surrounded by the oxygen, the negative side of the water, while the side that was negative, which is the phosphorus, will be surrounded by the hydrogen side of the water molecule, which is the positive side for this polar molecule. So polar covalent molecules do not break apart. The whole molecule is pulled from the solid and then surrounded by water according to likes of charges. Okay, so you need to be able to explain these. And another example is sugar water. Sugar water is also a polar covalent molecule, and it will do the same thing. The side of the molecule that's negative surrounded by the positive of the water. The negative side of the water will surround the positive side of that sugar. So please notice that the polar covalent molecules do not split into charged ions. This molecule, any polar covalent molecule that's your solute, will not conduct electricity because there's no charges moving around in the water. The whole molecule is still together. They just have been pulled apart from the crystal they had formed or whatever. Okay? So here is side by side what we just talked about. Water, your universal polar solvent, dissolving an ionic compound, table salt, and here dissolving another polar covalent compound, sugar. And here the water pulled apart the ions. It broke apart the ions. The ionic compound has split. And each of the ions is surrounded according to likes of charges. Those are charges moving around can conduct electricity. So ions come apart. When you have a polar covalent molecule, the whole molecule is surrounded by water according to likes. So the negative side of the molecule surrounded by the hydrogens of the water. The positive by the negative side of the water, which is the oxygen. But the whole molecule remains together. The covalent bonds have not been broken by the water. And you need to know that. Now, how about liquids dissolving in other liquids? So liquid solute dissolving in liquid solvent. You already know that when you have a liquid, those atoms and molecules are farther apart than when you have a solid. There's more energy also in a liquid than there is in a solid. So it's easier for a liquid solute to dissolve in a liquid solvent. But it's also based on likes, on charges. A polar liquid solute will dissolve in a polar liquid solvent. An ionic liquid solute will dissolve in a polar liquid solvent, but it will not dissolve in a non-polar solute. For example, if you have oil, which is a non-polar solute in liquid form, it will not mix with water, which is a polar solvent. You're going to have two layers. Non-polar solutes that are liquid will only dissolve in non-polar solvent solutes. So just like when we did, it's the same reasoning that we did for the solid solutes. There has to be attraction between the molecules to dissolve one inside the other. So if there are charges and they're strong enough, it will dissolve. If there's no charges, there's no attraction, there's no dissolving anything. Okay? Now, gas. Pay attention to gas, page 358, because they work a tiny bit different than solids and liquids. When you have a gas, if your solute is a gas, there's a lot of energy in a gas. Those particles are being atoms or being molecules, have a lot of energy. They're moving around very fast. They are bumping into one another, and they're trying to expand. Okay, so for that solute to be dissolved, like in a liquid, when you were trying to do carbonated drinks, you need to pull those atoms and molecules in to the liquid. There has to be a very strong attraction between those atoms and molecules in the gas and the liquid in which they have to dissolve. If there's not that attraction, like magnets, okay? Strong attraction, it will not dissolve unless you help it. You can help it by putting pressure on the gas, which is what you do when you create soda pop. You already know that when you open a can, the gas will escape. It was pushed in by pressure into the liquid, but as soon as you open it and the pressure is lowered, the gas will try to escape, and it does escape. Okay. Table 11.1 in your textbook, page 358, summarizes how this works, and you need to know this. Solute phase can exist in a solid, liquid, and gas. Same for solutes and solvents. You need to be able to give examples. What are the requirements for dissolving? If your solute is a solid, the solvent molecules must be attracted to the solute molecules so strongly that the solvent molecules can get between the solute molecules or ions and pull them far apart from each other. So remember that. The first step is always to break them apart. If you cannot do that, you cannot dissolve it. Now, liquids are easy to dissolve with one another if there's attraction of charges. So they only need to be attracted to the solute molecule a little bit, because you don't have to really separate the solute molecules from a solid. They're already kind of separate. So the attraction needs to be there still. You have to have attraction, but not as strong as if you had a solid. Gases. The solvent molecules must be attracted to the solute molecules very strongly to pull the solute in towards that solvent. And you need to know these. Page 358, definition of solubility. What is that? Well, that is the definition of the amount of a given substance that can be dissolved in a certain amount of solvent. In chemistry, we talk about grams of the solute that will dissolve in 100 grams of solvent. So basically a percentage. Okay. For example, this is a soluble substance. Soluble means it dissolves in this liquid. It's floating around, it's surrounded by the liquid. This is an insoluble substance. It's not dissolved in this solvent. It's precipitating at the bottom. There you go. So we're talking solubility has to do with soluble substances. Substances that do dissolve. How much can you dissolve in 100 grams of that solvent? If we talk, an example that they give you is, if we say that we have a solubility of a 10 per 100, it means that you can dissolve 10 grams of whatever the solute is in 100 grams of whatever the solvent is. And that's all you can do before it precipitates. I mean, it still would have some of the solute dissolve, but then it would stop dissolving because it cannot hold any more of that solute. And you'll see more examples, okay? Don't worry about it. So the solubility, how much you can dissolve, how much solute can you dissolve in that solvent, depends on both the identity of the solute and the identity of the solvent. Examples. At room temperature, because you're going to see in a minute that temperature affects solubility. You're going to be doing an experiment about this as well. So at room temperature, if you have baking soda in water, so you have 100 grams of water in both cases, okay? Because solubility is given in 100 grams of the solvent. 100 grams of water can hold 12 grams of baking soda, but it can hold 37 grams of table salt. So it has more solubility. There's a higher solubility for salt than it has for baking soda. It can hold more salt per 100 grams of water. Now, if you change the solvent, now it's not water anymore, you have alcohol, the solubility of each will decrease. The amount of the solute you can put in that alcohol decreases. So solubility has to do both with the solute and the solvent. The attraction between the two of them, that should make sense. Okay, page 359, they give you the definition of saturated solution. So you have a solute and a solvent together, you have created a solution, and now it's saturated. So know the difference between unsaturated and saturated. Unsaturated means that the solvent is still taking solute. It can still dissolve solute, but it can do it up to a point. When it cannot dissolve any more solute, then you say that that solution is saturated. It cannot dissolve any more solute. So, saturated solution, a solution in which the maximum amount of solute has been dissolved. It will not hold any more solute. Now, this is important, please pay attention. Saturation of solutions. A solution that contains the maximum amount of solute that may be dissolved under existing conditions is said to be saturated. Existing conditions means the temperature and the pressure. That's what it means. You change that, you can change the saturation of the solution. And you'll see that shortly. A solution that contains less solute than a saturated solution under existing conditions is called unsaturated. So it's still taking solute. It can still take solute. A solution that contains more dissolved solute than a saturated solution under the same conditions is supersaturated. And you'll see how you can create a supersaturated solution in one of your experiments. We'll talk about it as well. Here you go. You have a solution. You have a solute suspended in that solution. It's dissolving it up to a point. It has reached saturation. When you have it super saturated, you have too much solute. It cannot dissolve anymore. That solute will go back to its original state, which was a solid, and precipitate. And that, I should say, its solid phase, and create a precipitate at the bottom. So if you see precipitate at the bottom of your beaker or your tube, test tube, that means that that solution is supersaturated. It's taken as much solute as it could take, and everything else is accumulating at the bottom. You're going to do experiment 11.1 this week. So you're going to see the effect of temperature on the solubility of solid solutes. We're going to talk about it in a minute, but we're going to talk in more detail when we meet on Friday for our Zoom meeting, before you turn in your lab report. And if you have questions, also email me during the week. You're going to do experiment 11.2, so the effect of temperature on the solubility of a gas. We'll talk about that here, so you kind of see what's going on, but also when you're doing the experiment, reason through what you have learned to explain why things are happening the way they are happening. Okay, let me see if I can move this so it's not covering that. Okay, what you need to know for right now, and let's think about this for a minute. The solubility of solids increases with temperature. So here you have solubility, and here is the temperature. As you increase the temperature, you can increase the solubility. So how many grams of that solute you can put in 100 grams of water. Because think about it. Temperature affects liquids more than it affects solids. So what are you doing when you give temperature to a solution? You're increasing the ability of that liquid to penetrate the solid and pull molecules apart. That translates to more solid being able to dissolve in that liquid. You have increased the solubility of that solute in that liquid. by giving it energy. Okay? On the other hand, when you have gases, what are you doing when you are trying to dissolve a gas into a liquid? You're trying to attract the gas in. But if you give energy to that system, to that solution, gas will be more affected by that temperature than the liquid will. Gas with more energy moves faster away from one another. Those are atoms or particles or whatever molecules you have, whatever gas you have. I mean, it could be oxygen, it could be carbon dioxide, whatever you have there. So by giving it more energy, you make it harder for that liquid to attract the gas in. The gas is trying to get away. More energy, more freedom, more movement. Okay? So it's going to be decreasing the solubility of that gas into that liquid. That temperature affects gases in reverse to solids. Okay? Liquid into a liquid. Basically, there's no effect because both liquids are being affected the same way. For right now, that's what you need to know. So we're not talking about liquids here. For right now, disregard the effect of temperature on liquids. Not affected enough to be interesting for right now. But solids and gases, you need to be able to explain what's going on with both of them. Ask questions if this doesn't make sense. Pressure effect. We talked a tiny bit about the effect of pressure on the gases. But how does pressure affect solids and liquids? Page 362. Pressure has little effect on the solubility of solids and liquids. So basically, pressure, you can disregard the pressure when we're talking about solid solutes and liquid solutes. But it has a very significant increase in the solubility of a gas. If you increase the pressure, you're pushing the gas particles down closer to the liquid. So it's easier for the liquid solvent to attract the solute in, that gas in. And you need to know that. You decrease the pressure, it's the opposite. The gas expands again and tries to escape. With this kind of information, you need to be able to do stuff or answer questions like the extra practice problem number 1 in page 579. So basically, just reason through questions like this. I'm going to read it to you. It says, you are having trouble dissolving a gas into a liquid. What should you do to increase the solubility of the gas? Well, think about it. If you want the gas to go into the liquid, think for a second. I'm going to tell you in a minute. You can pause right here and then go back and see if you were right in your reasoning. You want that gas to go into the liquid, what can you do? Well, you can increase the pressure. If you increase the pressure, you're pushing it towards the liquid, and the liquid more easily will capture or attract those gas atoms or molecules. So increase the pressure will increase the solubility of that gas. You also know that temperature affects liquids in reverse than solids. So the more temperature, the less solubility for that gas, more energy to escape. So decrease the temperature. Make the temperature cooler. If you decrease the temperature, the gas has less energy to escape. The atoms or molecules get closer together, and it's going to be easier for that liquid to attract it in. So those are the things that you can do. Increase pressure and or decrease the temperature. Now, you are also going to do experiment 11.3 on page 363. Investigation of the solute that releases heat when dissolved. So you're going to see in a minute that some solutions, when you dissolve solute in a solution, give out heat, and some of them take in heat. So some of them feel hot, some of them feel cold. So let's talk about that. They have names. Exothermic versus endothermic processes. And that has to do with solutions and also chemical reactions. Well, yeah. Exo just means out. Endo means in. So exothermic processes is a process that releases heat into the surroundings. So if you were to touch this beaker, it would feel hot to the touch because it's releasing heat, and both chemical reactions and solutions can do that. And actually, you're going to be doing an experiment in which you're going to be doing this. On the other hand, endothermic processes are processes that absorb heat from the surroundings, and when you touch that beaker, you feel it coolish. So it's going to be cooler than the environment. And that has to do also with chemical reactions are also going to be exothermic and endothermic, and we're going to be talking about this again when we do that. You need to know how cold packs and hot packs work. That's explained to you on page 364, figure 11.6. Let's talk about cold packs, because hot packs are the reverse of a cold pack. Instant cold packs that look like a plastic bag, like this one right here, are filled with a liquid. When you heat it and shake it up, it gets extremely cold, and then you put it on your bruise or any part of you that's hurting, okay? The liquid inside the cool pack is water usually. In the water is another plastic bag or a tube that contains ammonium nitrate fertilizer. And when you heat the cold pack, it breaks that tube or that extra bag that's inside. And then it mixes with the water, creating a solution. This mixture creates an endothermic reaction. So it's a reaction in which heat is absorbed from the surrounding area, and it feels cool to the touch. It absorbs heat. The temperature of the solution falls up to about 35 degrees Fahrenheit for about 10-15 minutes. So the pack is cold for 10 to 15 minutes. Endothermic process will create cold compresses. Exothermic reactions will create the hot packs that you also can use on a sore muscle. People like to put hot packs when you have sore muscles. So know the difference. Cold packs, endothermic reactions, or you're creating a solution that's endothermic, and the hot packs is the reverse. It's an exothermic reaction or exothermic solution. Okay? And this concludes the first half of Module 11. So read your textbook, add to your notes if you need to. You can watch the video again. You don't have any on your own this week, but you have a lot of labs. So ask questions if you need to. We're going to go over the experiments on Friday during our Zoom session. Study for your quiz. There's a lot of new terms, lots of vocabulary here, and study for your test. So that concludes the first half of Module 11. Have a good week, and I'll see you Friday.